Hi everyone, today we're going to talk a little bit about hypothesis testing and null hypothesis testing. I want to talk about this in relation to the statistics that we've done and that we're going to be doing, just in general terms, because much of this hypothesis testing is the same. The theory and philosophy behind hypothesis testing is the same. However, we're going to be using different tests to infer things from different types of data. We talk about categorical data, so we use specific tests for categorical data. We talk about continuous data, so we're going to use different tests for that kind of data as well. So we want to make sure that we understand how hypothesis testing actually works. So I'm going to refer back to some slides that I have used about hypothesis testing, and then we'll get into a couple of things from the internet and my whiteboard, if I can shift my webcam over for everyone to see it. So the first thing we're going to talk about, what is hypothesis testing? And I'm going to switch over to share the screen from these slides. Okay, so everybody should see or not see. Let me check to make sure this is working. I don't think it's working as smoothly as I would like. Okay. So here we have the difference between the null and alternate hypothesis. And typically when we do hypothesis testing, we're testing two things. The first is a null hypothesis that said there are no changes, no correlations, no anything. It's kind of boring. We're saying that there's no relationship between two variables, or more than two variables, or changes between means of two variables. So what's the importance of that? Well, the reality is that by testing the null hypothesis, we're able to falsify. And if we falsify the null hypothesis, and we talk about falsification as a way of determining what's left. If we falsify the null hypothesis, then typically we assume that we can find evidence in support of an alternative hypothesis. And as you can see here, in an alternative hypothesis, we see changes, we see correlations, we see that two variables are linked, or that there is differences between two variables. So typically when we formulate alternate hypothesis, we formulate those alternate hypotheses as saying there is a difference. And if we reject the null, then we typically accept or find support for the alternate hypothesis. So this is the reason why we use null hypothesis, is to falsify it, to say that there are no differences, no correlations, so forth. So it's fairly simple. There's a hypothesis and alternative hypothesis. Okay. And again, this is true. And if the null hypothesis is not true, then we reject it. And again, we typically provide support of the alternate hypothesis, which is the one that says there's a difference. So we look to see if there's no difference, and if we accept there's no difference, we support the null hypothesis. Otherwise, we reject the null hypothesis. And we do this using a rejection region of the sampling distribution. And to find the rejection region of the sampling distribution, we use alpha, which is a measure of significance. And to find what the region actually is relative to the statistical test that we're using, we try and find the critical value. So when we set alpha at 0.01 or 0.05 or 0.10, that corresponds on a distribution table with a critical value. So typically we're given a distribution table. This is not something that we have to make up or anything like that. If a distribution table is necessary, typically it will be given or will be available on the internet, or will be in a textbook, or will be on a handout, or so forth. So we know that these can correspond with critical values. We typically assign these values as a level of probability of certainty of which we accept from our sample, making an inference about the population. So what this is essentially saying at 0.05, which is a standard that most researchers use in most instances, is that if we were to sample randomly from the population 100 times, we would see that we would accept the null hypothesis 95% of the time, or reject it 5% of the time. Okay, so what does that actually mean? It means that we're accepting a certain level of certainty in making that inference. Then 95% of the time our example will be correct, and 5% will be incorrect, and we would need to accept the alternate hypothesis. So again, I've mentioned here that it's selected by the researcher at the beginning. So the researcher accepts the level of risk. But as we've talked about in other terms here, if we accept one risk, we trade off versus another risk. We trade off type 1 error versus type 2 error. The idea of trading off a false positive, where our research shows the alternate hypothesis is true, and if the alternate is true, then we reject the null, versus the reality of the population in which the null hypothesis is true, versus the false negative in which our research shows the null hypothesis is true, but the reality is the alternative hypothesis is true. So we make these trade-offs, and that's what part of what makes marketing science a science, is that we make these levels of trade-offs to determine how we actually go about testing the null versus alternative hypothesis. So in this instance, we're going to be using 0.05, and in most instances, we'll be using 0.05. Again, as I mentioned before, these levels of significance correspond with a critical value for a specific statistical test. So what do I mean by that? The critical value is the cutoff point that shows us where we reject the null versus where we reject or accept the null. In null hypothesis testing, when the p-value is less than 0.05, we reject the null hypothesis. Or I will put here in other terms, when p is greater than 0.05, we support HO. Okay, so this makes sense. When p is less than our critical level of significance, we reject HO. So when p is greater than our critical level of significance, we support HO. So what happens when the p-value of the null hypothesis test is 0.02? Well, 0.02 is less than 0.05, so we reject the null hypothesis. How about what happens if the level is, the p-value is 0.657? Well, at 0.657, it's greater than 0.05, so we would support the null hypothesis. So again, these probabilities, these levels of significance correspond with p-values. Okay, so let me bounce back to my things here. So we take here for each statistical test, and again, some statistical tests deal with categorical variables, some statistical tests deal with continuous variables. We have these tables, and we're given the critical value tables that correspond with p-values. So as you can see here, this t-distribution we'll talk about in the future corresponds with a p-value, and this chi-square corresponds with p-values up here. So alpha here is 0.995. That will be a left-hand side of the test. 0.990, 0.975, all the way switch over to the right side of the distribution. P of 0.100, 0.05, 0.025, 0.010, and 0.005. These correspond with all of these critical values. Okay, so what exactly does this all mean? Well, let me switch back over to one of these things, these graphics, where we talk about the critical testing or null hypothesis testing of chi-square. So in this test, we see at 0.05, let's say, that there is a critical value here. And anything that is less than the critical value, we would fail to reject the null hypothesis. Or in layman's terms, we would call that accepting the null hypothesis. And anything greater than that would be rejecting the null hypothesis. Okay? So let's say the critical value, I'll go back to this distribution table, the critical value, can pick something random, is 9.348. So I'm going to switch over to the whiteboard for a second and try and draw one of these things on the whiteboard. Let's see if this works. Okay, so we have a chi-squared distribution that looks like this. Here we have our critical value. Okay, and we have this critical value. Let me see this. I'm not quite sure why this is inverted. Apparently the webcam has decided to invert what it is, how it is I'm actually appearing. But if we have this critical value here, and we say this is alpha, and alpha equals 0.05, this is CV, critical value. Let me see if I can move this up a little bit so you can see. Okay, so this is the critical value. This could be any number that tells us what the rejection region is. And again, this is the rejection region. The critical value is the number at alpha. And we normally, again, is up to the researcher, but we normally set alpha at 0.05. So this number, if we're using a distribution that has 1 degree of freedom, and we'll get to degrees of freedom in a second, if it was 1 degree of freedom, it will be 3.84. That number defines the rejection region of the null hypothesis. Okay? So any number that is greater than this, we reject. And any number that is less than this, we would accept. Let's bring this back to p-values. If this is 0.05 and we are rejecting it, then what p-values would we be looking for? We would be looking for anything where p is greater than 0.05. Sorry, p is less than 0.05. So 0.04, 0.03, 0.02, 0.01. All would be rejected under the null hypothesis. Right? What does that mean logically for accepting the null hypothesis? Well, that means anything that is on this side would be greater than 0.05. So it would be alpha or p is greater than 0.05, 0.06, 0.07, 0.61, and so forth. So we are essentially saying that we accept the null hypothesis if it is p greater than 0.05 and p is essentially all the way to 1. P is less than or equal to 1. On the other hand, we reject it if p is less than 0.05 and p is greater than or equal to 0. Okay, does this make sense so far? On the critical value side, if we accept over here, and this is 0 to 3.84, then what does that mean? Well, that means any test statistic that is less than the critical value will accept the null hypothesis. Any test statistic that is greater than this value will reject the null hypothesis. Okay? So we said for 1 degree of freedom on a chi-square test that the critical value, the value, statistic value that defines the rejection region is 3.84, 3.841. So that means if we run a chi-square test and we get a value of 0.821, 821 is less than 3.84. It's to the left of our critical our region defined by the critical value, our rejection region. So we would then accept the null hypothesis. Let's say instead that our test statistic for chi-square is equal to 10.963. 10.963 is way out into here and into the rejection region. So these critical values correspond with p-values. So we can tell if we have a critical value and a test statistic whether or not we need to reject the null hypothesis, but we can also translate the test statistics back to p-values and see whether it's greater than or less than 0.05. So, why is this important? Well, because as we do hypothesis testing, we need to know whether or not we accept or reject the null hypothesis. whether or not we are saying there is a difference, or rather, there, in null hypothesis terms, there's no difference, no relationship, no association between variables. Okay, so let's jump back for a second to this. So you can see here that we can fail to reject over here. There's a critical value of chi-square that corresponds to the p-value, which the researcher typically sets at 0.05, and then the rejection region here. So this critical chi-square, the test statistic can be anywhere, but our rejection region is defined by this critical value. So let's say we had a test where the degrees of freedom were 2, and we set our rejection at critical value at 0.05. Well, if that was the case, we would look for 2 degrees of freedom by 0.05 alpha, and we get 5.991 as our test statistic. So any value less than 0.5991 would be accepted, and anything greater than 0.5991 would be rejected. It would be in this rejection region. Okay? This is going to go the same for any other statistical test that we use. Now, we use different distribution tables for different statistical tests, but this idea of a critical value aligning with a significance level is the fundamental thing to understand. For instance, again, here's the t-table. If we set something at alpha of 0.05 and we had 1 degree of freedom, our critical value here would be 0.6314. When we test the null hypothesis, anything less than 0.6314 would be accepted, and anything greater than 0.6314 would be rejected. So hopefully this makes a little bit more sense between the critical value of a statistical test and the probability or alpha level or level of significance of that test when we deal with null hypothesis testing. Okay? Now, one of the things that we've talked about is this idea of splitting into 2 critical value regions. And we do that when we are testing whether or not a hypothesis is equal or equal to, as opposed to a less than or greater than hypothesis. So I will switch over to this slide, for instance, and you can see here this null hypothesis tests whether something is equal versus unequal. So we take the level of alpha, which again would be 0.05, and we do what's called a two-tail test. We're testing on the distribution between both sides. So we would divide 0.05 by 2, and this would then be 0.025, and again, 0.025 and 0.975. One more time, that's because we're dividing the 0.05 by 2. On this side, it would be 0.05 divided by 2, and this would be 1 minus 0.05 divided by 2. So I'll actually show you that here. Okay. And I'll actually show you that here as well. On an upper tail test, we're saying that the null hypothesis is less than or equal to, so we want to have the rejection region over here, as we've done. And on a lower tail test, we want to have the rejection level is greater than or equal to down here on the other side. Okay, so what is this actually saying? What's the point of this? Well, because typically we do things with two-tailed tests, and the reason is because we do have a level of uncertainty. So it actually didn't manage to. Okay, so let me do that again. Okay, so we see here the level of significance on a two-tailed test. We have here mu, or the population mean, is equal to 3 versus the population mean is not equal to 3. And because we don't have a level of certainty about this equivalence, we typically do alpha 0.05 divided by 2 on this side and 1 minus alpha divided by 2 on this side. So usually 0.975. When we have more certainty or we use certain distributions, we typically do an upper tail test. And so that would be when something is less than or equal to or greater than is an alternate hypothesis, and that would be alpha. And then the reverse of that is 1 minus alpha for the lower tail tests. So for chi-square, usually we're using upper tail tests. So usually we're using alpha is 0.05. Okay? Okay, so what does that mean? Well, you can see here that this looks like a one-tailed test at 0.05. But if we were to do a two-tailed test, and we set alpha at 0.05, what do we need to do? Well, a two-tailed test needs to be divided by 2. So 0.05 would then be 0.025 on one side, and 1 minus alpha divided by 2 would be 0.975 on the other. So our critical values for a two-tailed test of 1 degree of freedom would be 0.001 and 5.024. Again, these critical values define the rejection region. Anything greater than 0.5024 would be rejected. Anything less than 0.001 would be rejected. And everything in between we would accept for the null hypothesis. So hopefully this starts to make sense. The same thing occurs with a t-distribution, or an f distribution, or a chi-square distribution, any other distribution that we can think of. Here we have critical values of a bunch of things. So what happens if we want to make, which we typically do, a two-tailed test of a t-distribution? Well, we have alpha as 0.05. We divide it by 2. So we would have 0.025 on the top end, defining the critical value. And we would then subtract on the other side. But again, typically when we're doing this, we're using the upper tail probability. And you can see right here it says upper tail probabilities. Okay, so what exactly does this mean? Well, again, as we discussed, we're talking about our critical value regions here, that we reject the null hypothesis when p is less than 0.05. We accept the null hypothesis when p is greater than 0.05. We have a critical value at 0.05. We accept the null hypothesis when we're less than the critical value. We reject the null hypothesis when we're greater than the critical value. And this should be, again, because critical values correspond to levels of significance. And we find this using a distribution chart that will be given to us. Okay, now one of the things that I've mentioned when we're talking about a chi-square test is this idea of having degrees of freedom. And when we talk about degrees of freedom, in general terms, that means how many parameters are set by our statistic that will allow us to find out how many other parameters can vary if one is missing. This is a very technical term. So again, what you would need to know in this instance for a chi-square statistic is that the amount of degrees of freedom there are rows or number of what's the word I'm looking for? The number of categories in one variable minus 1 multiplied by the number of columns or the number of categories in another variable minus 1. So if I have something that has 4 categories to it, what might have 4 categories? Income level. So let's say we're doing income level as a categorical variable. Then we would do 4 minus 1, and we would multiply that by the columns. And how many, what's another categorical variable that we might use? Income level and car brand purchased. So let's say there are 5 different car brands. So 5 minus 1, 4 minus 1 is 3, multiplied by 5 minus 1 is 4, equals 12. So if we're doing a chi-square distribution of income and car brand with 4 levels of income and 5 car brands, then 4 minus 1 times 5 minus 1 is equal to 12, and we have 12 degrees of freedom. When we look at our distribution table, we can find that the degrees of freedom are listed usually on the vertical axis. And then we correspond those degrees of freedom with our significance level. So what is it that we're actually trying to say here? We're actually trying to say, again, whether or not there are differences between groups. So if we were looking in this chi-square test at whether or not income level is related to car brand, finding the degrees of freedom with a test statistic that will give us information, and then relating a p-value to a critical value will determine whether or not income level is related to car brand. So let's say, again, these are hypotheticals, but let's say we had here 12 degrees of freedom. Well, what would we do? Well, I'm just going to switch over for a second to distribution table I have here, and screen share. Okay, so you see here the distribution. Let's say we set the critical value at, we said the degrees of freedom, let's say the level of significance was 0.05. Okay, so alpha is 0.05. We said that it was going to be 12 degrees of freedom. So 12 degrees of freedom at 0.05 is equal to 21.026. 21, switch back. So 21.026 is now our critical value. 21.026 is our critical value of the chi-square test for 12 degrees of freedom. And again, we're testing the relationship between income level of categories of income level and car brands. So we had 4 income level categories, 5 car brand categories, and that was 12 degrees of freedom. 12 degrees of freedom, we used 0.05. We found the critical value at 0.05, 12 degrees of freedom, 21.026. Now, let's say we use our chi-square statistic, and we have that chi-square statistic as a formula. I'm not going to go through the formula again because we're really focusing on the hypothesis testing in this particular tutorial. If it was 21.026, when would we accept and when would we reject the null hypothesis? Well, we said that this was the critical value, that this would define the critical region of rejection of anything that was p less than 0.05 and p greater than 0.05. So what does that mean? That means a test statistic that was between 0 and 21.026 would be accepted. Anything that was greater than 21.026 rejected. So let's say I have all of these observations and frequency counts, and I calculate the chi-square statistic. What is the chi-square statistic? Well, let's say it calculates out to 8.652. 8.652. Is that greater than or less than the critical value? Well, it's less than. It's in our accept region. And we could translate, if we use a distribution calculator, 8.652 to a p-value. And that p-value would tell us whether or not it's greater than or less than 0.05. But we can see by the statistic in the critical value that it's less than, that it's in the accept region. Let's say we have a bunch of data, we calculate our observed and our expected values, our frequency counts, so forth. We square, blah, blah, blah. We find the chi-square statistic. What's the chi-square statistic in this instance? The chi-square statistics is 42.691. Well, where is that relative to our critical value? It's greater than our critical value. It corresponds with a p-value or a significance level. And so therefore we would probably reject the null hypothesis. Great, so we've talked about rejecting, accepting the null hypothesis. In this hypothetical example, what does that actually say? Well, our null hypothesis is that in this instance, H null is that income categories are related to, or there is no association between the income categories and brands. So HO equals income not related to brand. That would leave the alternative hypothesis, income and brand are related. If I accept the null hypothesis, I'm saying that income is not related to the brand. If I reject the null hypothesis, then I typically am supporting the alternative hypothesis and then say that income and brand are related.
So it's easy to talk in abstract terms about what accepting and what rejecting the null hypothesis means. But what we're also looking for is what the actual hypothesis is, and what happens when we accept the null hypothesis, and what happens when we reject the null hypothesis. Now, when we use SPSS to show us statistics, we usually get the test statistic. They leave it up to us to find the critical values. They give us the test statistic of all of the data. And then typically what they give us is a p-value of significance. And that kind of can be confusing because the p-value that they give us is not the null hypothesis p-value. It's a p-value, but not for the null hypothesis. Well, it does. It tells us whether or not the null hypothesis is accepted or rejected. But it does that relative to the alternate hypothesis. So while we're testing the null hypothesis to try and falsify it, what we're also trying to do is provide evidence in favor of the alternate hypothesis. After all, if income is not related to the brand, do we really care? Well, maybe not. Maybe we do want to see what relationships exist between income and brand. So we use the alternative hypothesis instead.
Okay, so let me go switch back to a particular group of handouts that I was looking at. I don't have anymore. Okay, so
what happens? Well, we have this acceptance and rejection region. But what happens when we take this statistic? We want to find what happens with the mean. And now the question is there a difference? So the alternative hypothesis is here. H0, H1. Now we're trying to demonstrate where there's a difference of means. And this is why we control for type 1 versus type 2 error, because here we have type 2 error, and here we have type 1 error. Type 2 error is a lot bigger in this instance. And if we're rejecting the null and we're supporting the other, then what happens? Well, we see with SPSS, they give us a hypothesis and a p-value. And let's say that the p-value is 0.000. And it typically says significance testing. What are we testing for significance for? We're testing for significant differences between two variables, between two groups, between two responses. So the thing about those values that SPSS gives us is they typically tell us when p is less than 0.05 that we're accepting the null hypothesis. Reason this out for a second. If p is less than 0.05, what do we do with the null? We reject it. And if p is less than 0.05 and we reject the null, what do we do with the alternative? We tend to accept it or say we support it. So what SPSS does is it gives us the p-value, and we can reject or accept the null hypothesis, but we also flip it around and reject or accept the alternate hypothesis. And if we accept or reject, if we use that p-value, it's sometimes easier to look at it in terms of the alternate hypothesis. So let's say I get an output for this chi-squared of brands versus income levels. And I want to know what happens when I get a p-value in SPSS of 0.356, 0.356, okay? Because usually SPSS gives us 3 decimal places. If the p-value is 0.356, I would then reject the alternate hypothesis. And the logical explanation is, if I'm rejecting the alternative, then I'm supporting the null. But go back again, if p is less than 0.05, we reject, but if p is greater than 0.05, we accept the null. What was p? P was 0.356. P356 is greater than 0.05, and so therefore we would accept the null. So again, it's this looking at it one way and then looking at the reverse. The null hypothesis is always relative to the alternate. So if p is less than 0.05 and we reject the null, then we also are supporting the alternate. And if we're supporting the alternate, then we're typically finding a difference between groups, or an association or a correlation or something that shows that there is a relationship in some way between groups, and that relationship is significant. So again, to recap what we've talked about hypothesis testing in terms of accepting the null and rejecting the null. We've talked about it relative to significance levels of p less than 0.05, which is a standard that a lot of researchers use. But again, that is up to the researcher to decide the level of certainty by which he wants to use. So we typically use 5 as in 5%, as in 95% certainty and 5% bias, or about 5% error. We talked about the correspondence between that level of significance and a critical value, and that we use a table to find the critical value at a particular level of significance, a particular alpha. And if we find that critical value, that defines the rejection region. And anything to the right is rejecting the null hypothesis, and anything to the left is accepting the null hypothesis. If we find that critical value, we can compare the critical value to the test statistic. Again, because of the relationship between a critical value and p-value, or alpha. The critical value is alpha. And then we find the p-value of the test statistic, the probability of the test statistic to happen 95% of the time out of 100 sample times. Okay, so we talked about that. We talked a little bit about two-tailed tests and one-tailed tests. Typically, when we use chi-square, we're using a one-tailed test. But if we need to do a two-tailed test, we would divide alpha by 2 and then go find the critical values at one end of the tail and at the other end of the tail. And then we talked about how to relate that with degrees of freedom, particularly for this chi-square statistic. So there's a lot of information that statistical tools can use to determine whether or not we accept or reject a null hypothesis. And ultimately, statistics is about hypothesis testing. It is about finding whether things are the same or whether things are different, and whether we can infer that things are the same between our sample and the whole population, or different from our sample and the whole population. So hopefully this clarifies a little bit more about how to do hypothesis testing and how critical values correspond with alpha, and how p-values can correspond with test statistics, and that by understanding the relationships between those ideas, we can then do the hypothesis testing to find out meaningful information for developing marketing strategy. So Until the next time, that's it for now.